Hi, my name is Daniel Lejeune, and in this video, I'm going to talk to you about ensemble methods and how they are implicitly regularized. Specifically, I will talk about the regularizing effect of subsampling in ensembles of ordinary least squares predictors. Ensemble methods, like random forests and boosting, are typically among the best performing off-the-shelf machine learning methods. There's lots of empirical evidence for this, but we don't have much theory explaining why ensemble methods perform so well. In this work, we take a step towards better theory for ensemble methods. Specifically, we consider the effect of random sampling of the data in non-adaptive ensembles. So, you should think about ensembles like random forests, where each learner is independent, rather than methods like boosting. Of course, random forests are ensembles of decision trees, but to keep things as simple as possible, instead of using decision trees, we consider ordinary least squares predictors for each member of the ensemble. What we find is that when we consider such an ensemble, with random sampling and non-adaptive ordinary least squares predictors, when we tune the amount of feature subsampling in the ensemble, we achieve the same risk as the optimal ridge regression predictor, suggesting that feature subsampling has a ridge-like regularizing effect. I'll get into our specific results later. So we are given a data matrix X, and our goal is to predict the target variables Y using linear combinations of X with coefficients beta. For each member of the ensemble, we will have access to a subsample of the rows, or examples, governed by the subsampling matrix T, as well as a subsample of the columns, or features, governed by the subsampling matrix S. We will take this subsampled data and learn the corresponding coefficients using ordinary least squares. For the next member of the ensemble, we will collect an independent sampling of the data, and similar for the next, and so on. To be slightly more formal, we have an n by p data matrix X and a vector of ground truth coefficients beta. We receive training target variables Y generated by x beta plus sigma z, where z is a standard normal vector. We want to construct an ensemble predictor for Y that is equal to the average of k individual predictors, and each individual predictor is trained by ordinary least squares on the subsampled data. For the subsampled data, we assume the sampling strategy samples all rows and columns with equal probability and produces submatrices having an expected size of eta n rows and alpha p columns, with the additional constraint that the submatrices produced have more rows than columns so that we can solve ordinary least squares uniquely. We study the out-of-sample risk of this learned predictor, which is the expected squared error of prediction using an independent sample x. I won't go through the entire derivation of the risk here, but the ability to compute the risk comes from the ability to break down the risk into sum of pairwise interaction terms. This brings us to our first result, which I will state here informally. Assuming the entries in X are IID standard normal, and the norm of beta is 1, then if we take the limit as n and p go to infinity with the ratio of p over n going to a constant gamma, we can obtain an expression for the expected risk of an ensemble of size k. Notice that the row subsampling factor eta only appears in the second term, which decays with the ensemble size, implying that row subsampling has a vanishing effect on large ensembles. Now let's take the limit as k goes to infinity to consider a very large ensemble. This leads us to our next result. If we then optimize this expression with respect to alpha, or the column subsampling factor, what we obtain turns out to be the same as the optimal ridge regression risk. Of course, it is well known that ridge regression is optimal for this problem. That is, it minimizes squared error. So, by ensembling, we can optimally regularize the solution with a ridge-like regularization. If you want to know more about this work, I encourage you to check out our paper, where we include more such as plots demonstrating convergence and discuss things like the connection between ensembling and dropout. I would like to thank the agencies that sponsored this work, and most of all, thank you for listening.